So this video is about algebra of matrices. These are basically things you can do when you have many matrices with you. So the very first thing that you can do is check equality of two matrix, and this is a bit this is something which we looked upon in the previous video, but we said we will talk about it in the next video. So this is it. We say two matrices are equal when first of all they should have the same size, that is they should have the same number of rows and same number of columns, and once this condition is satisfied, then you can check for the entries, corresponding entries, that they should have the same corresponding entries. So if this condition is itself not satisfied, then you can definitely say that the two matrices are not equal, so you need not check about the equality of the entries. So when I have these two matrices, let's say this is a 3 row 2 column matrix, so I can say it's a 3 by 2 matrix, and this is a 2 by 3 matrix, 2 rows 3 columns. So you can see straight away that the size is not same. So this is a 3 by 2 matrix, this is a 2 by 3 matrix, the dimensions don't match, so I can say that these two matrices are not equal. So although their entries look very equal, this is a 1 2 1 2 3 4 3 4 5 6 5 6, but since their dimensions are not same, I can say that these two matrices are not equal. So if I were to have a matrix equal to this matrix, I would have to have an exact copy of this matrix. So if I have a same dimension matrix, I have a 3 by 2 matrix with the same entries 1 2 3 4 5 6, then I can say that these two are equal matrices, or these two matrices are equal. So yeah. Next thing you can do with matrices is you can add matrices, and of course the first condition is that they should be of the same size. Only then you can talk about its addition. And then if you have the confirmation that they are of the same size, then you can say that the resultant matrix will have the entries as a term by term addition of your individual entry and individual matrices. So if I have this 1 2 3 4 5 6, this is again a 3 by 2 matrix, so I can say it's a 3 by 2 matrix, and I have another matrix here 9 8 6 7 0 2. This is again a 3 by 2 matrix, so they have the same size, this is the same dimensions, 3 by 2 3 by 2. So I can talk about its addition. Yes, so I can add these two matrices, and the result will also be a matrix of the same dimension. So I'll have a resultant matrix of the same dimension, it will be a 3 by 2 matrix, and the entries will be the term by term addition of individual matrices. So here if I have 1 and here if I have 9, so the addition will give me 10, and similarly if I have 2 here, 8 here, the addition gives you 10. 3 plus 6 gives you 9, 4 and 7 gives you 11, 5 and 0 gives you 5, I'm sorry, and 6 and 2 gives you 7. So this is the resultant matrix. This is the matrix you get when you add these two matrices. Very simple definition. The only condition is that they have to have the same size, and the resultant matrix will have that same size. The next thing you can do with matrices is multiply them with a scalar. Now a scalar is just a number. It's a number. So you can multiply a matrix with a number like this. So if I have a number 9, and I can have any matrix here, any size of any matrix. This is a 3 by 2 matrix again. So my resultant will again be a 3 by 2 matrix, and the entries in that matrix will be what you get when you multiply this number with each and every entry here. So if I multiply 9 with 1, I get a 9. 9 2s are is 18, 9 3s are is 27, 4 times 9 is 36, and 5 times 9 is 45, 6 times 9 is 54. So this is the resultant matrix when you scalar multiply a matrix with this scalar. This is the resultant matrix. The other thing you can do with a matrix is take the transpose of that matrix. So if you have a matrix like this is a 3 by 2 matrix. Its transpose is usually denoted by A with a capital T above it, and this is again a matrix. I can call it a new matrix B, but it is nothing but the matrix you get when you interchange the rows and columns. So when you make the rows into the columns and the columns into the rows, that's what you get when you take the transpose of a matrix. So if this is a 3 by 2 matrix, my transpose will be the opposite of that. It will be a 2 by 3 matrix. So it will have two rows. So it will have two rows and it will have three columns. So this will be a 2 by 3 matrix. It will be a 2 by 3 matrix. And if I had the first column here to be 1, 3, 5, that will now become my first row here. So if I have a 1, 3, 5 here, I'll have a 1, 3, 5 here. And if I have a 2, 4, 6, so this will become a 2, 4, 6. And you can also say that the first row became the first column, the second row became the second column, the third row became the third column. So basically the rows and columns get interchanged. And a very good enough result to you can even declare from this is that if you have a matrix and take its transpose and then take the transpose of that matrix, you'll get your same matrix back. So you'll get your A back. So if I have this matrix, I take its transpose, I get this. If I were to take the transpose of this, again my rows will become the column. So this row 135 will become the column 135, and this row will become the column 246. So I'll get my same matrix back. So if you do the transpose twice, it's you'll get the same matrix back. Now this very simple operation gives rise to many beautiful definitions, many beautiful matrices. These are special matrices called symmetric matrices, and these are particular types of square matrices. These are those square matrices which do not change when you take the transpose of that matrix. So if you have a matrix and you take its transpose, then the two matrices are equal. So if you have a matrix being equal to its transpose, we know what transpose is, we know what equality is. So if you have a matrix which is equal to its transpose, so you can say that that matrix is a symmetric matrix. And a good way to check just by looking at a matrix is it is symmetric about its diagonal. So if I have a square matrix, first of all, it needs to be a square matrix. It is a subset of square matrices. So and I can have any entries in the diagonal. So let's say I have a 1, 3, 2, and for this to be symmetric matrix, this needs to be symmetric about the diagonal. So whatever entry I have here needs to be the entry that I have here. So let's say I have a 0 here, then this needs to be a 0. Let's say I have a 5 here, so the diagonally opposite entry is a 5 here. This needs to be a 5. And let's say I have a 7 here, so and the diagonal opposite entry is a 7 here. So you can check that if I have this matrix and I take the transpose of this matrix, so if this is A, then A transpose is nothing but this is a 3 by 3 matrix. I'll have a transpose as a 3 by 3 matrix. And if the row here is 105, my column here will become 105. The row here is 037, my column will become 037. And if the row here is 572, the column will become 572. And indeed, you can check that these two matrices are the same because first of all, their dimensions are same. And each and every corresponding entries is same. 105, 105, 037, 037, and 572, 572. So this is what you get when you take the transpose of a symmetric matrix. A good way to check is that if you forget about the diagonal, the opposite entries should match. So 0 here, 0 here, 5 here, 5 here, 7 here, 7 here. If that is the case, then you can say that this matrix is a symmetric matrix. Now, I'll give you a convoluted way of saying that a matrix is symmetric matrix. It's just a very technical definition. It says that Aij is equals to Aj for all I and j in the possible range. It just means that if you interchange the row and the column, the entry should not change. So if I were to look at let's say this entry, then this entry is in first row, second column. So if I were to interchange the row and column, if I were to look at the second row and first column, I should have the same entry. So this is just one convoluted way of saying the same thing. In layman's language, you just need to check whether it is symmetric about the diagonal. So if you have the entry here, it should be the same entry here. The other special kind of matrix is skew symmetric matrix, and again it is a special kind of square matrix. In layman's language, if I were to say, it is a matrix A, which when you add its transpose to that matrix, it gives you the zero matrix back, the null matrix back. So I'll give you an example. If I have a 2 by 2 matrix, a 3 by 3 matrix, let's say. Now here you'll see that why diagonal entries need to be 0. You'll see why the diagonal entries all need to be 0. If I have an entry, let's say here 4, then I need to have its negative on the opposite side. So if I have a 4 here, I need to have a negative 4 here. If let's say if I have a 3 here, then its diagonally opposite entry should be a negative version of that number. And if I have, let's say, 1 here, I need to have a negative 1 here. So if I have a here, this is A, then its transpose, A transpose, will be again a 3 by 3 matrix. This is a 3 by 3 matrix, its transpose will be 3 by 3. But the row here, 0, 4, negative 3 will become the column here, 0, 4, negative 3. The row negative 4, 0, negative 1 will become the column negative 4, 0, negative 1. And the row 3, 1, 0 will become the column 3, 1, 0. And what happens when you add these two matrices? If you add 0 to 0, it gives you 0. So if I were to write the addition, A plus A transpose. First of all, the addition is well defined because this is a 3 by 3 matrix, this is a 3 by 3 matrix, so addition is well defined. It will be a 3 by 3 matrix again. And I just need to find the corresponding entries. 0 plus 0 gives you 0. 4 and a negative 4, it indeed gives you 0, and this is why you see why it needed to be the negative version of that number. The diagonally opposite entry needed to be the negative version of that number. So again, so if you see negative 3 added to a 3 gives you 0, negative 4 added to 4 gives you 0, 0 added to 0 gives you 0. So this again shows you why the diagonal entries had to be 0, because if the diagonal entries was anything else other than 0, then you would have be adding that same entry to itself when you take the transpose. And if it was non-zero, you would get a non-zero entry here. So that wouldn't satisfy the condition for the result being a zero matrix. So that's why it was necessary for the diagonal entries to be all zeros. So let's move forward. -1 added to a 1 gives you 0. A 3 added to a negative 3 gives you 0. 1 added to negative 1 gives you 0. 0 added to 0, of course, gives you 0. So you see that the resultant is a 0 matrix. It's a 0 matrix of order 3 by 3. And if you add its transpose, you get a 0 matrix. And this shows that this matrix, my original matrix, is a skew symmetric matrix. And also you can say that its transpose is a skew symmetric matrix. But what is important is this matrix is a skew symmetric matrix. And again, a convoluted way of saying this would be to say that Aij is equals to negative of Aji for all I comma j possible values of I comma j. So this just says that if you interchange the row and the column, your entry should become negative. So if I were to look at this entry, 4 is at the first row, second column. So if I were to look at the second row, first column, it should be the negative version of that number. So if I have a 4 here, this should be negative 4, and vice versa and similarly for all the other entries. And this also shows that if I were to have the diagonal entries, for the diagonal entries, I is equals to j. So if I had to have I is equals to j, I would say aii is equals to negative of aii. And a number is equal to its negative only when it is 0, right? So I can say that aii is equals to 0. So this is another way of reasoning out why the diagonal entries needed to be 0. But this is what a skew symmetric matrix is. What you need is diagonal entries should be 0, and the opposite entries should be negatives of each other. So if this is 4, this is -4, this is -3, its opposite is 3, it's -1, its opposite is 1.